get to start. Okay. Okay. Fine. So good morning. Today we are going to start with this unit 3, which is on centrifugal pumps. So if you look at the syllabus, so we have kept it sweet and short, where we'll be discussing on the different parts of your centrifugal pump and different heads, we call it as pressure heads, associated with your centrifugal pump, and some of the efficiencies. And there is something called as a minimum starting speed required to start your centrifugal pump. And there is why we go for why there's a reduction in the pump capacity when it is delivering the fluid, that we call it as a slip. And maybe nowadays I think priming is most of the pumps what we get is from the technologically they are all improved. We have what is called as self-priming pumps, but still we should know what exactly is priming. Then the cavitation, which is a very common phenomena which happens, and we have to look into that why that cavitation occurs. So then there is something called as maximum suction lift, and there is something called as we are called NPSH. Okay, that means we need to have this seat where I can place this, pump to have the seat. We have something called as a maximum suction lift. Okay, that maximum suction lift is required for the pump to work safely. Okay. Then net positive suction and what we call it NPSH, that's very much required. So if I'm able to place your pump at that particular some minimum to lower limit to upper limit actually. So most of the pumps what we place or what we design, it based on the NPSH. See, we try to buy a pump from the from a marketplace or something. At that time, they try to go what is called as maximum suction lift they go to give. That is your upper specific limit, where I can place your pump from the sump level. Now, you can't, sometimes you may be not in a position to place at that particular level, you may be placing at a lower level. So, how lower you can go? So, there is a lower limit. So, between this upper limit and lower limit, whatever you have your pump you are going to install, that we call it as net positive suction head. That we call it as NPSH required. It is what as a manufacturer will decide upon, centrifugal pump manufacturer will decide upon, and NPSH available at your installation place. So both the things we'll try to discuss. It's a very good phenomenon. Most of us, we have centrifugal pumps at home. We can go and verify this. Whatever we have installed at home is fine, or whether it needs some kind of an improvement, all those things. Then again, when we will go for multi-staging. So multi-staging centrifugal pumps, one to get higher pressure, or the higher pressure rate, and the other one is with respect to wherever I want lower higher discharge. So two things we'll try to discuss. Okay. Now, when you come to the schematic diagram or construction of a centrifugal pump, so I have given both the side view as well as the maybe front view. Now, so this is a common centrifugal pump. What I have taken the sketch from what is available at your home. Okay. So two things I have tried to what we call it as maybe shading actually. So you have a motor. So why we have a motor? Because it's a power absorbing device. It has to be connected to some kind of electric motor, whatever it is. So it has a motor. From there, it is coupled. So shaft is coupled to your pump. Okay. So because of this length of the shaft, it has to be properly balanced. So I do have what is called as a bearings. Okay. I have bearings. Then see the whole thing has to be placed on some kind of a base which should be a solid in construction to avoid as much as possible the vibrations has to be reduced. And usually this bed or base is made of concrete, and is all your pump as well as motor, everything, they are bolted. Okay, they are bolted to it, and it's usually T-bolt or something which we will see, and they are bolted, and they are completely, it should be on a base, actually base or concrete beds to avoid the vibrations. Okay, now coming to the pump side, what are the parts it has? So it may be having a suction pipe. Okay, you can see there is a suction pipe. So in the suction pipe, if you look at it closely, it has a footwall. See, at the bottom of this particular thing, I am going to have a footwall. Okay, what is this footwall? It is a a strainer or it is a filter. So it's a strainer or a filter. So most of the pumps over a period of time, what we try to do, if the pump is not running to the full, we try to look at the foot valve as the first thing, because there may be something clogged, something dirt is, maybe dirt is stuck in the filter. So what we try to do, if possible, we'll try to remove the foot valve and try to clean it. If it is not possible to clean it after maybe not, what we will do, we try to replace the foot valve. Okay. Now, if you closely observe, the footwall should be completely immersed in your sump. Why it has to be immersed actually? And one more thing is actually, this footwall is a non-return valve. So fluid can flow in only one direction, and fluid can't flow from pump to your sump. So fluid can flow from sump to your pump. So fluid, your footwall is a non-return valve, and it's a strainer. It may be having a filter. It's going to filter all the dirt and all, so that the clean water enters your. Okay. The pipe connecting your footwall to the eye of the impeller is called as suction pipe. Okay. Now, at the eye of the impeller, the fluid is sucked. Okay, that is called as suction. And usually, we may be having a gauge over there, a pressure gauge near the suction or at the eye. So that we can call it as suction gauge. So usually the suction gauge or suction pressure is negative, slightly below your atmosphere. Okay, slightly below your atmosphere. Because if you, what is the pressure in your sump? It will be atmospheric, and a slight below. So I need to create a small delta P. A small delta P has to be created between your sump level or sump and your eye, so that fluid is sucked by the at the eye of the impeller. So the fluid is sucked and it goes in. So once the fluid goes in at this particular point, what will happen? Because of the centrifugal action, okay, that's why it is called a centrifugal pump, the fluid will start gaining some amount of kinetic energy. Okay, that's what I'm trying to show using the side view of your impeller. Okay, once the fluid starts coming out, what does the fluid? Fluid will gain some amount of kinetic energy. There is a kinetic energy, there is a centrifugal energy at the same time, and there is some little bit of relative energy. All these energies are there. Now, what is required at the delivery? At the delivery, I want everything to be converted to some kind of a momentum, or we call it as pressure head. So what we try to do that, to convert that all the energies to pressure head, we try to put it in a casing. Okay, we try to put the whole pump in a casing. So what is the purpose of casing? Casing is something like, you can see that they're all diverging. I've written an arrow, which is, if you can see that it's increasing, it's diverging. So this diverging casing, or we call it as a scrolled diverging, maybe the area wise, if you look at it closely. So this will increase, this will try to convert your kinetic energy to corresponding pressure. So static pressure. So the static pressure, with that pressure head, fluid will try to come out of your pump. And if I want to measure the pressure at that particular point, I can put a pressure over there that will give your, so if I put the pressure gauge over here, what does this give? It will give your delivery pressure. Okay, I do have a suction pressure here. By putting a pressure gauge which is negative, this will be negative and this will be positive. Okay, now, so there is a pipe. See, once this particular thing, so I can control the flow. See, whatever that is coming out of your centrifugal pump, by putting a valve over here, say like this, by putting a valve, so this is your valve, I can control what is the amount of water that should be thrown out or that should be pumped out. So that is called as delivery valve. So then the pipe connecting from your delivery exit of your pump to your tank is called as delivery pipe. Okay, the pipe connecting your exit of your centrifugal pump to the tank is called as a delivery pipe. A simple see, what I'm trying to show here is actually, I shown a simple construction of your centrifugal pump. So it has a sump, it has a footwall, it has a suction pipe, it has a impeller, then it has a delivery valve, it has the gauges on the suction side as well as on the pressure side, and it has a delivery pipe, and it has a shaft coupled to a motor which is placed on a concrete bed or base to absorb all the vibrations. So simple, you can write in your own words and you can write. Now, whatever I showed on the left hand side, this particular this thing, so little bit of blown view I have showed, that is with an diffuser blades. See there, if you look at this particular thing, I don't see these particular, I don't have any diffuser blades here. Here, if you look at it, I don't have any diffuser blades here. Because diffuser blades are used only whenever I am trying to use a centrifugal pump for higher pressures. Now, if you look at the construction of this one and the construction of this one, so this is used for high pressure liquids, where I have something called as exit guide vanes, which are after your impeller. I'm going to put that actually just before your casing. So I'll be having what is called as your exit guide vanes or guide vanes are this diffuser blades. Okay, these diffuser blades are exit guide vanes which will try to convert your kinetic energy to static pressure. Right? So here in the first case, it was only your casing was converting your kinetic energy to static pressure. But in case of a high pressure system, I will be using the guide vanes as well as your casing. So the conversion takes place in two steps. One in your diffuser blades, or we call it as exit guide vanes. The second one is your casing, where the kinetic energy gets converted to delivery pressure. So this is about your simple schematic or construction of your centrifugal pump. Okay. Now, next thing what we are supposed to look into is actually different pressure heads. Pressure heads associated with centrifugal pump. With centrifugal pump. Okay. Now before that, I have put a simple sketch. I am trying to show you a simple sketch here. Okay. Now, this is your central line. See, I am trying to show this is your central line. So, this is the central line means this is the point where you are trying to install your pump. I am trying to place my pump actually. Anything below your pump and anything above your pump is what I am trying to look at. Okay. Now, you have a sump or water level, water at the bottom, and you need to see what is the purpose of the pump actually. I need to pump the water or take the water from your low level tank, we call it as a sump, to the high level tank, that is called as a tank, or to a higher level. Okay. Now, you have something called as a sump, which showing a triangle, which is the sump level. Okay. From the center of the pump to the sump level, whatever I have, that length we call it as your suction head. Okay, the height of that particular thing, or it is the head from the surface of the sump to the eye of the impeller, because central line, this is where I have the eye of the impeller. Okay. That means it is the head from the surface of the pump to the eye of the impeller or central line of the impeller, whatever it means. Now, what is HD? That is your delivery head. It is the head from the eye of the impeller or from the central line of the impeller to the delivery tank water level. Delivery tank water level. So you may be wherever I have the delivery. So this is I have a triangle here. This is the delivery tank water level. So wherever I have that height or head we call it as delivery head. Okay. Now these two heads are very important. That is suction head and delivery head. Now there are other things also there. See, whenever I have a pipe, so either on the suction side or on the delivery side, there is a little bit of friction. Okay, there is a little bit of friction. What is the purpose of this friction? This friction will reduce your pressure creation. Okay, now I try to put this or represent the friction loss or HF, friction head loss on the suction side like this. That is HFS. That is frictional loss on the suction side. So what is it actually? It is a loss of pressure head on the suction side of the pump. So similarly, I can have a loss of head on the delivery side of the pump. So loss of head on the delivery side of the pump, it is called as frictional loss on the delivery side. So HF is the frictional loss. To represent the suction, I put a subscript S, and to represent on the delivery side, I put D. So HF is the total friction. So I can call it as friction loss on both suction and delivery side. HF is equal to HFS plus HFD. Okay. Now, there is one more thing. What is it actually? I have been telling you that your velocity at the exit, that means the velocity of the fluid entering the tank should become zero. But that is very rarely happening. What we see is actually, suppose if I try to deliver the fluid at the maybe to into the tank at the some bottom or something, then I can tell that velocity is almost becoming negligible. But the velocity, what will happen? See, it's something like I have a tank, like let me show you. Say I have a tank at the top like this. So now you have a delivery pipe. Your delivery pipe will go something like this, and the fluid will start going into tank. Now there is some velocity V2 at the exit. So your delivery velocity is not zero. There is some kind of an exit loss. So that I call it as, if I try to represent in terms of head, it is V square by 2G. So V is energy level, it is V square by 2. So if it is with respect to head, V square by 2G. So now it is at the delivery, it is VD or whatever V deliver also the delivery, I call it as VD square by 2G is the exit. We call it as, it is the exit loss or fluid at the exit. Now, at the same time, suppose the fluid, see, suppose the tank is something like this. The fluid is entering the tank in this fashion. Usually they won't do. This is very rarely they do. Then what will happen? The velocity here is also the VD is almost zero. VD is becoming almost zero. That means that I can have a construction of this form or a construction of this form. So for one case, kinetic energy at the exit is almost zero. Another case, there is a little bit of exit loss. Okay. Now, what about your suction velocity? Suction velocity has to be zero because I am trying to take the fluid from a sump which is stagnant. Okay, the fluid is stagnant or it may be very negligible. So the suction velocity is almost zero because of that your suction head is also zero because the fluid is sucked from the stationary fluid in your tank. Okay, in your sump we call it as, in the sump the fluid is almost stationary. That's the reason why your Vs is almost zero. Now let us try to write whatever we discussed now, that we'll try to write one by one. Okay, let's start with the frictional head. Let me start with frictional head, that is HF. Okay, so here as I told you have two things. One is HFS. Okay, that is head loss due to friction on the suction side. Okay, so in this we have, so frictional loss on the suction side. On the suction side. So if I want to define it, so what it is actually, let me define it. It is the loss of head, okay, on the suction side of the pump. On the suction side of the pump. This is your HFS. So similarly, I have HFD, which is called as frictional loss on the delivery side. Delivery side, which if I try to write it, this is actually HFD. This is loss of head on the delivery side of the pump. Okay. Now, what is the total loss? H frictional loss. That is HF is equal to HFS plus HFD. Okay. This is about your whatever we have. Now, the second thing. What is actually? This is the first one. Now, the second one. Suction head. Okay. We call that as a suction head. Suction head, which is S suffix yes. What is it? It is the head from the surface. It is the head from the surface of the sump. It is the head from the surface of the sump. Okay, surface of the pump sump to the eye of the impeller, or you can call it as the center line of the pump. Center line of the pump. So here the most important thing is actually it is eye of the impeller and the surface of the sump. This is your HFS. What is the third thing? It is your delivery head, which is H suffix D. What is it actually? It is the head from the eye of the impeller. It is the head measured actually. It is the head measured from the eye of the impeller, or central line of the pump, okay, to the water level in the delivery tank, okay, to the water level in the delivery tank. So this is the definition for your suction head and delivery head. Okay. Now what else is there? I told that you have other thing, that is Vd square by 2g, or Vd square by 2g, what I showed here, Vd square by 2g here. What is it actually? It is the kinetic head. Okay, kinetic head loss. We call it as kinetic head loss. Kinetic head loss. We call that as V square by 2g. What is it actually? It is the loss at the kinetic loss. It is the exit loss of the fluid. Exit loss of the fluid. So what about the other one? I told that. So you have as the fluid is stationary, as the fluid is stationary, The fluid is stationary in the sump. Okay, your suction velocity is 0, or therefore the suction head, that is Vs square by 2g, is also 0. That's the meaning of it. So I don't have any entry loss of the fluid. So I do have the exit loss, which is exit connect. So these are the losses associated with, or some of the heads are associated with your simple thing. Now, based on this head, we have two more heads actually. One is an ideal one, other one is the actual one. Okay. Now, hope you remember, we defined what is called as an Euler head. Okay. So when I was doing the derivation for the Euler's energy equation, I have defined that. So we have another one which is called as Euler head. What is it actually? Euler head. So usually this is defined by H suffix E. Euler head, which is actually He is equal to your work done per specific volume by G. So work done per specific work divided by G, or I can call it as VW2 into U2 minus VW1 into U1 by G. So what is this actually? This is nothing but your Euler's equation, which already we have derived it. Suppose in this I have a special case. If my whirl velocity at the inlet is 0, if VW1 is 0, that means no whirl at the inlet, then your He will be equal to VW2 into U2 by G. So if there is a whirl velocity, I have to use He is equal to VW2 into U2 minus VW1 into U1 by G. If there is no whirl velocity and then let VW1 is equal to 0, then it is VW2 into U2 by G. So this is about your Euler head. And I do have one more practical working head. Okay, that is called as manometric head. Okay, let me define that. Okay, that is your manometric head. So this is H suffix M. Okay, what is this actually? This is the head under which your pump will work. What is your manometric head? Head under which the pump will work. Pump will work. Now let us try to write it actually. So now when I come back to this particular thing, if I try to add up all the things, I'll be getting my working head of your centrifugal pump. That is HFS plus HS plus HD plus HFD plus VD square by 2G. If I add up everything, I'll be getting what is called as your manometric head. Okay, let me write that. Okay. Now, what is this manometric head? HM is equal to your friction loss after suction plus your suction head plus your delivery head plus your friction loss at the delivery head, that is D, plus your kinetic energy loss, that is Vd square by 2G. And here we have made an assumption that Vs square by 2G is equal to 0. Otherwise, that also I need to add it. But 99.99% of the times your suction velocity is almost 0. Now, see, usually people try to combine this actually. See, HFS and HFD, they combine together to call it as HF. Okay. At the same time, they try to combine HS HD to call it as H. That is your working head. The suction head plus delivery head is represented by small h. See, here what I try to do is HF is equal to HFS plus HFD, and your small h is equal to HS plus HD. Anyway, you need not worry about this actually. This is your losses. This is your losses. You need not worry. Now I can rewrite my equation as HM is equal to, okay, your HF plus H plus VD square by 2G, where H is equal to HS plus HD and HF is equal to HFS plus HFD. And few books actually, let me write that also. So instead of suction, they call it as 1. So this is a note actually. So I'm trying to write note. 1, they take it as suction side, and 2, they take it as delivery side. In that case, I can write my HM as, okay, HF1 plus HF2 plus H1 plus H2 plus V2 square by 2G. This is how they write actually. This is HF, this is small h. The only difference is actually they try to write in terms of 1 and 2 instead of your suction and deliver. This also is fine. So this is about your different heads associated with your centrifugal pump. Okay. Now we need to look at some of the efficiencies, so which we already know. So when I try to look at the efficiencies associated with centrifugal pump, what type of machine it is actually? It is a power absorbing machine. So I want to supply the energy to the fluid. Okay, so as I say, I'm going to supply AC. It's going to take the energy. How you are supplying? The first thing is I'm going to supply the energy to the shaft, and the shaft will supply the energy to the rotor. The rotor will transfer the energy to your blade, and blades will transfer the energy to your fluid. Okay, that's how the energy transfer takes place. So overall, if you look at it, this is a purely a power absorbing machine.